Today we're covering 4-6, which is talking about relative motion between objects that are both moving along the same axis. First we need to just talk about vocab. So this book and other books and the AP exam are going to talk about a reference frame, which is just referring to the fact that all motion in our universe is relative to something. And common language talks about this too. So if you are stating your opinion, people will ask, well, what's your point of reference? Where are you coming from on that, basically? Okay, because everyone, you could say, has bias in their opinion. Okay, so everything in the universe is moving. Therefore, when you state that something is moving, you need to say relative to the fact that you are moving also. Okay, so you can see these two pictures here that an observer on Earth would see the sun move across the sky over the course of the day. If an observer was in a spaceship, then she would see the person on Earth rotate underneath her, whereas she might see the sun relatively holding still because of her position. So when we talk about reference frames, we are choosing a location that we describe motion from, knowing that that location is also moving, from someone else's perspective. Okay, so these two pictures, I hope once you take a closer look, will make sense to you. And I also have a video that we can look at that shows the same idea. When a package is dropped out of this airplane, we see in the top picture what it would look like from the pilot's reference frame. So because the pilot is dropping the package, and the package had a velocity that went with the plane. The package is a projectile, but from the pilot's perspective, it seems to drop straight down from the plane, like an object in free fall. Okay, so you can see this red circle is supposed to represent like the package, and it's splashing down into some water. So it looks like straight vertical motion to the pilot. But if someone is using the ground as a reference frame, for instance, they're standing on an island or something and watching this happen, then they're going to see the bottom picture. They're going to see a parabolic path for that projectile with that red dot moving through space. Okay, so if we would like to do some math here, there's a vector formula for calculating relative velocities. Really, I could, these were marked in your book without the little vector formulas, without the little arrows over the V's. But they can include signs, so I'm a little confused about why they didn't put the arrowheads over here. Okay. Let's talk about what the subscripts mean. So if we're talking about VPA, that means the velocity of particle P with respect to reference frame A. So let's say the package with respect to the airplane, okay, equals the velocity of the package with respect to reference frame B plus the velocity of reference frame B with respect to reference frame A. So actually it would be better if we talked about something horizontal to begin with. So rather than talking about the package with respect to the airplane, it might be better to talk about some riverboat problems is what they're called in physics. And so I'll get into an example here with math in the next slide. But this star here is important, that the two frames, A and B, must be moving at constant velocities relative to one another. So the airplane needs to be moving at a constant velocity relative to the ground, for example. Or if in the next example we'll talk about a boat and the ground. So we can't have something that's accelerating, otherwise this relationship is not going to hold true. Okay, so let's do an example. We have a boat moving relative to the water. Okay, and so I'm going to maybe draw this vertically. So here's our river. Let's see here. Let's pretend the current is going this direction. Okay, so this is going to be 2 meters per second, and this is going to be the velocity of the water, W, with respect to the ground, G. Okay, and I'm going to make that negative because I guess usually I have it south as negative. So I'm going to say this is negative 2 meters per second. Okay. Then the boat is going to go, it's going to make a round trip. All right. So, and it's got to go from one dock to another dock. Let me change colors here. So let's draw some docks in here. So we've got here's a dock here, and here's one over here. And it's going to go downstream so the boat's going to go from, oh lordy, this is a bad looking boat. From here, okay, down, and then it's going to turn around and go from upstream the other way, right? That's its job. And when it does that, it can go, the velocity of the boat with respect to the water is 10, okay, meters per second. Oops. All right. So now, when we have to add these, I should note, though, that on the way upstream, that's a positive, right? But then when it's going downstream, then that's a negative 10. Okay. So, let's follow our rules here. And the pattern of the letters, okay, in our equation, sorry, let's go back to the slide with the equation. If you want to write this correctly, notice that it goes PA equals PB plus BA. So it's kind of like the B's have to cancel in here. All right, that's the way the equation has to go. So when you write this, please make sure that your equation matches that pattern. So let's make sure it does here. I want the velocity of the boat with respect to the ground. And I think that should be equal to the velocity of the boat with respect to the water plus the velocity of the water with respect to the ground. And the W's would cancel, quote unquote, like in the middle there. Or they match each other. They're both lined up in the middle. So that matches VBG then is what I'm going to get when I add those two. All right, so then this is a correct equation. I can do this. Now, as it goes downstream with the current, isn't it going to go faster? Like, doesn't the current help? Okay, so then I'm going to do boat with respect to water, -10, plus water with respect to ground, okay, is -2. So then the boat with respect to the ground, if you're standing on the side watching this boat go by, you're going to see it go south or whatever at 12 meters per second. That makes sense. Okay, then as it goes upstream, let's write that. It's going to get same equation. Let me write that again. Boat with respect to water plus water with respect to ground. But now the boat has changed direction. So now it's going against the current. That's what upstream means. So now it's got a velocity of +10. The current is always going -2. So now its velocity with respect to the ground is 8 meters per second positive, which in our world means like north at 8 meters per second. Okay. And then it asks, how long does it take the boat to make the round trip? Well, they do tell us the distance between the docks, right? But we're gonna have to do this in 2 pieces, right? So let's do the downstream. Then I know that I'm doing velocity. This is a constant velocity equals the change in x over the change in time. So then I'm saying I've got a velocity of -12, and that I'm going down south basically, -1,000 over the change in time. So then multiply both sides by delta t, divide both sides by -12. Oops. So I get this part took 83 seconds, and then the upstream part, I only got to go 8 meters per second. I went north 1,000 meters. All right, do the same thing. Okay, then I got more time, right? Because I'm going slower, 125. And then add those up for a total of 208 seconds. Okay. All right, so then this last one I would like to talk about in class and have you write the equation. Make sure you can write it in this format and decide on some subscripts for this example.